Metabolism. It's defined as the total amount of all anabolic and catabolic reactions in a cell or organism. Living organisms must continually capture, store, and use energy to carry out the above processes. All forms of energy can be classified as either kinetic energy or potential energy. Kinetic energy is the energy of moving particles or objects, so a heart contraction. Potential energy is stored energy. It's the energy of position, i.e. chemical bonds or the attraction of electrons to protons. There are two laws of thermodynamics. The first law of thermodynamics is energy can be neither created nor destroyed. It can only be transformed from one form to another. The second law of thermodynamics is the amount of disorder, or entropy, in the universe always increases with any change that occurs, and at the same time, the energy that can do useful work decreases. It gets lost as heat. In chemical reactions, entropy increases when solids become liquids or gases, there's a fewer number of reactant molecules, and they form a greater number of product molecules. Complex molecules are broken down into simpler subunits, polymers into monomers, or glucose into carbon dioxide and water, or when solutes move from diffusion. So, potential energy diagrams. Activation energy is the amount of energy needed to strain and break the reactant bonds. Transition energy is a temporary condition in which the bonds within the reactants are breaking and bonds between the products are forming. Energy is released when product bonds are formed. So exothermic means you give off energy or heat as heat. Endothermic is when heat is being used. And those are the two types of reactions. Exothermic or exergonic, if more energy is released during bond formation than was during bond breaking. The result is a net energy output equaling the exothermic reaction. This type of reaction can also be referred to as an exergonic reaction, as mentioned previously. It occurs spontaneously, therefore it is favored because it increases entropy. Products contain less energy than the reactants, therefore they're more stable. Usable energy is released. It's a decrease in free energy available. So to get a picture of what an exothermic energy diagram looks like for potential energy, it's biking up a little bump to go down a huge hill. It's doable to bike up that little hill because you get to ride down the hill, and it's a huge hill, so it'll be fun. So it's worth your time and effort. An endothermic or an endergonic reaction. It occurs if the amount of energy absorbed from breaking reactant bonds is greater than the energy released in the formation of products. This results in a net absorption of energy. This type of reaction can also be referred to as endergonic reactions. It does not occur spontaneously and is not favorable because they involve a decrease in entropy. So it's a decrease in randomness. Products contain more energy than the reactants, and it requires an input of usable energy. Example, ATP needed to drive reactions. So it's like the opposite of what an exothermic is. You have to go up the huge side of the hill only to go down a little bump at the end. It's not worth it because you're using too much energy. And also, we can describe entropy as a deck of cards. When you throw up a deck of cards in the air, it increases randomness, which it'll make the entropy higher, rather than when you have them sitting in the box, it's less entropy.